Good morning. Today we will see differential phase shift gain. Already we have seen the binary phase shift gain. In binary phase shift gain, we have seen the coherent system and non-coherent system. So first of all, we will see what is meant by coherent system and what is meant by non-coherent system. So the coherent system is the system in which the phase and frequency of transmitter should be matched with the phase and frequency of receiver. This type of system is called as coherent system. The second is the non-coherent system. The non-coherent system is the system in which phase and frequency is not matched with the phase and frequency of receiver. Then in binary phase shift keying, only coherent receiver is present, non-coherent receiver is not present. This is the limitation of binary phase shift keying. Means for the non-coherent system, the binary phase shift keying is not applicable. And to overcome this ambiguity problem of binary phase shift keying, we will go for the differential phase shift keying. So this is the basic difference between binary phase shift keying and a differential phase shift keying. Okay. Then here the name is the differential phase shift keying. Why the name is given differential phase shift keying? Because in differential phase shift keying, we will consider the present input bit and previous transmitted bit. So that's why the name is given the differential phase shift keying. Okay. So here in this phase, the block diagram of differential phase shift keying transmitter is shown. It consists of logical network. That logical network consists of XOR gate and delay of 1 bit, that is TB, and the output of XOR gate is given to the balance modulator. Okay, so these are the two main block, that is logical network and balance modulator. So with the help of this block diagram, we will see the operation of differential phase shift keying transmitter. Okay, so according to this block diagram, as we have seen here, the two inputs is applied to the XOR gate. The first input applied to the XOR gate is the input data, that is D of t, and the second input applied to the XOR gate is the previous transmitted bit, that is B of t minus TB. With the help of delay of TB, we have taken the previous transmitted bit, that is B of t minus TB, and it is applied as input to the second input to the XOR gate. Then D of t XOR with B of t minus TB, and we will get the output of XOR gate, that is B of t, and the output of XOR gate, that is B of t, is applied as input signal to the balance modulator, or the first input signal to the balance modulator. And the another input signal to the balance modulator is the carrier signal, that is C of t, and we have taken here carrier signal C of t is equal to under root 2ps cos omega ct. So the input for the balance modulator are the two inputs. First one is the output of XOR gate, that is B of t. Second one is the carrier signal C of t. And then that balance modulator multiplies these two signals, and it will give us the output of differential phase shift keying, that is S of t. Okay, so with the help of waveforms, we will see how the output waveform of differential phase shift keying will be generated. So here that equation number 1 shows that output of XOR gate, that is B of t, is equal to D of t, that is input data, is XOR with B of t minus TB, that is the previous transmitted bit. It is shown in the equation number 1. Then here equation number 2 shows the output of differential phase shift keying, that is S of t. S of t is the multiplication of B of t and C of t. As we know that B of t is the output of XOR gate and C of t is the carrier signal. So equation number 2 shows that D of t XOR with B of t minus TB into under root 2ps cos omega ct, that is the general equation for the output signal of transmitter of differential phase shift keying. Okay, so after that we will see the operation of differential phase shift keying with help of waveforms. It is shown in following waveforms. So here the first waveform is of D of t. So for the example, we have considered the input data d of t, that will be first bit is 0, then second one is 1, then 0, then fourth one is 1, fifth one is 1, sixth one is 0. So 0 1 0 1 1 0, that is the input data we have considered for the as example. Okay, so then the second waveform is of b of t minus tb. Then if you consider at initial condition the previous bit, that is b of t minus tb is 0, then we know that the output of XOR gate is the b of t, and b of t is equal to XOR of d of t into b of t minus tb. And as we know that according to truth table, the output of XOR gate will be logic 0 for the same bit, and will be logic 1 for the different bit. Means if the 0 0 is input there, then output of XOR gate will be 0. If the 1 1 is the input for the XOR gate, then output of XOR gate will be 0. If the different bits means 1 0 0 1 is the input for the XOR gate, then output of XOR gate will be high, that is logic 1. Okay, so according to this, as we have considered the first bit of d of t as 0, and initial condition, if you have considered first bit of b of t minus tb is 0, then output of XOR gate, that is b of t, will be 0. Then that output of XOR gate b of t, that is first bit is 0, is considered as a previous bit or the previous transmitted bit for the next bit of d of t. Means if you consider the next bit of d of t, that is 1, and for that here we have considered the previous transmitted bit will be 0, that is carry forward from the b of t. So for the next bit, the d of t will be 1, b of t minus tb will be 0. So according to the XOR gate, 1 0 will be 1 as the output of XOR gate, that is b of t. Then that 1 will be carry forward for the third bit of d of t. So third bit of d of t will be 0, then b of t minus tb will be 1. So 0 1 will be 1, then it will be next carry forward, and the fourth bit of d of t will be 1, and b of t minus tb will be 1. So 1 1 will be 0. In this way we will get the output of XOR gate, that is b of t, that is the third waveform. Then as we have seen the operation, in operation we have to see the b of t is the output of XOR gate, and that b of t is applied as input signal to the balance modulator, and as the second input applied to the balance modulator is the carrier signal, that is c of t. So that balance modulator multiply the b of t with the carrier signal c of t, and that waveform number 4 shows the carrier signal waveform, and with the help of that balance modulator, this b of t and c of t will be multiplied, and it will gives the output of differential phase shift keying. Okay, so if you consider the first bit, so with the help of that b of t and c of t, we will draw the waveform of s of t. So if you first of all you consider the first bit, that is b of t and c of t. As b of t is 0, that is logic 0 means low, and for that the s of t will be start from negative, that is from negative to positive. When at the end of first bit of b of t, the second bit of b of t will be 1, as first bit is 0, the second bit is 1, means it will be changes from low to high. So there will be a phase changes of our carrier by 180 degree. Okay, because at the end of first bit b of t, it will be changes from logic 0 to logic 1, means the phase of carrier changes by 180 degree. So for the duration of complete second bit, it will be then by changing the phase of 1 degree, it will be same as carrier signal. At the end of second bit, the third bit is also 1, means there is no changes from low to high or high to low, means the waveform will be waveform of s of t will be continue up to the end of third bit. Again at the end of third bit of b of t, the b of t changes from high to low, means there will be again phase changes of 180 degree. So for the duration of fourth bit, it also same, and again at the end of bit number 4, it will be changes from low to high. So again there will be phase changes by 180 degree. So whenever there is a changes in b of t, that is from low to high or high to low. According to that changes in b of t, there will be a phase changes in the output of differential phase shift keying by 180 degree. Okay, and so the phase of carrier signal, so here the phase of carrier signal changes according to the b of t, and that is of 180 degree. So in this way we will get the output of differential phase shift keying in transmitter of differential phase shift keying. Okay, the next part we will see the receiver of differential phase shift keying. Thank you.